Welcome back. So far, we've learned a little bit about plotting, and we've also learned a little bit about n-dimensional arrays and what that means. But truly, we've only just started scratching the surface of what's possible with Matplotlib and NumPy. In this lesson, we'll dip our toes into the power of something called a universal function, or ufunc for short. A ufunc is a concept in the NumPy library of a function that is able to run through every element of an ND array to transform the shape of the array, usually in some mathematical way. We'll look at an example of this. Let's start by making a new notebook in Google Colab. So once again, if you already have a notebook open, you can do that by going to File, New Notebook, or you can go to the Google Colab homepage and create a new notebook from there. Let's name this notebook ufuncs.ipynb. Like we have before, we'll use this first cell to import NumPy as np and matplotlib.pyplot as plt. And when you run that cell, hopefully you should see that green check mark. Then go ahead and make a new code cell. In here, we'll again use the plt.linspace function to make an ND array of evenly spaced values. And this time, we're going to generate values that are between 0 and 2 times the value of pi. And we know that pi is roughly 3.14, so 2 times that is going to be roughly 6.28. And we want to generate 10 total points, so we set that up like this. And if we print this value and run the cell, we can see an array of 10 numbers that are evenly spaced between 0 and 2 times pi inclusive. The reason that we're making points between 0 and 2 pi is because we want to make one complete sine wave. So we're borrowing knowledge from the mathematical field of trigonometry that tells us that's what we need to do. We're going to use these points that we just generated as our x-axis, and we'll feed them into a universal function, a ufunc named sin, sin, in order to generate our y-coordinates. Let's do that now. Add a code cell, then we'll set y equal to np.sin of x, like this. So sin is a universal function from the NumPy library that will take all the values in our ND array of x that we gave it, and it will figure out how to generate the corresponding y values for each x value to create a sine wave. And it will return to us a new ND array containing those y values. If we print y here and run the cell, we can see the array that's been generated. But will it really plot a sine wave? Let's find out. In a new cell, we'll call plt.plot once again, passing in x and y, then run the cell. You should see an output like this, which is a little rough looking, but you can see that it's basically a sine wave. How can we smooth out this sine wave? Well, it needs more data points. Let's make a new cell, and in there, add variables for resolution and frequency. We'll set resolution to 100 and frequency to 2. Then we'll use the resolution variable for the number of points on our x-axis. So instead of just 10 points, we're going to use 100 points of resolution. And we can multiply our array of x values by our frequency variable in the np.sin function. And you'll see what this does in a moment. We'll call plt.plot once again, passing in x and y. Go ahead and run the cell. Now here you see the results, which is a much smoother curve because we have more data. And we now see 2 complete cycles, 2 sine waves, because we multiplied the frequency by 2. We can play with those numbers to get a sense of how frequency and resolution affects the graph. And let's take note of something really important here. We can multiply ND arrays directly, and that's a really powerful feature of an ND array. When we multiply an ND array, it performs that operation on every item in the array. We can also add or multiply two ND arrays together. Let's take a look at that. Go ahead and add another code cell, and we'll make two new ND arrays. One will be called y1, and we'll set it equal to np.sin of x times 6. And the other will be called y2, and we'll set it equal to np.sin of x times 9. And then we'll call plt.plot, and we'll pass in x and y1 plus y2 like this. And now, if you click Run Cell, you should see a slightly more complicated and maybe even more lifelike version of the previous graph. It's almost starting to look like a natural wave, right? Or maybe like a graph of tides moving in and out, or of a sound wave. In the next exercise, we're finally going to start working with real-life data in the form of sound data.